Tonight, we're going to look at one of the strangest answers the James Webb Space Telescope has produced to one of the strangest questions in modern astronomy. The little red dots, those mysterious objects that JWST has been finding by the thousands at the edges of the observable universe, are not what almost anyone predicted they would be. They are not distant galaxies. They are not small quasars. They are not simply compact, star-forming regions at high redshift. They are something else, something that by every careful description no astronomer working in the early 2020s had on their list of expected discoveries. The little red dots are, in the current best theoretical interpretation, black hole stars. The phrase sounds like science fiction. But the framework behind it is, by every careful estimate, serious theoretical physics. It was developed by Mitchell Begelman at the University of Colorado, starting around 2010. It has been extended by Kohei Inayoshi at Peking University, by Roberto Maiolino at the University of Cambridge, by Andy Goulding at Princeton University, and by various other research groups in papers published over the past 5 years. The framework proposes that the little red dots are not galaxies at all in the conventional sense. They are something much stranger. They are direct, collapsed black holes in their growth phase, surrounded by enormous envelopes of radiation-supported gas that make them look superficially like compact, dust-obscured, accreting objects. But they are not dust-obscured. The redness comes from a different process entirely. They are not compact galaxies. The compactness comes from the structure of the radiation envelope. They are not accreting onto small black holes. The central black holes are, by every careful estimate, far more massive than the surrounding visible structure would suggest. The interpretation is, by every careful description, one of the most striking theoretical results to emerge from the JWST observations. It explains essentially all of the observed little red dot properties. It connects to the broader problem of how the first supermassive black holes formed. It suggests that the early universe was producing a class of objects that does not exist in the local universe at all. By the end of tonight, you're going to understand the original little red dot discovery, the specific observational properties that defied the standard interpretations, the Begelman black hole star framework and how it developed, the detailed physics of how a black hole can be surrounded by a radiation-supported gas envelope, the observational matches between the framework's predictions and the JWST data, the alternative interpretations that have been proposed, the implications for our understanding of early black hole growth, and what the next generation of observations will reveal about these strange objects. Before we get started, if you love exploring the depths of space as much as we do, take a second to like the video or subscribe. It's a simple action, but it helps this channel reach more curious minds like yours. Now, let's begin. Let's start with what astronomers expected the JWST observations of the early universe to find. The expectations were, by every careful description, specific and well developed. The Hubble Space Telescope had spent more than 3 decades observing the deep extragalactic fields. The deep field observations had identified thousands of distant galaxies at redshifts of 3 to 8, corresponding to cosmic ages of approximately 600 million to 2 billion years after the Big Bang. The detailed properties of these distant galaxies had been characterized in increasing detail through follow-up observations with various ground-based and space-based telescopes. The galaxies looked in the available Hubble images like extended, somewhat irregular structures with sizes of a few kiloparsecs. They had star formation rates of approximately 10 to 100 solar masses per year. They had stellar masses of approximately 1 billion to 10 billion solar masses. The connection between the galaxies and their central supermassive black holes, where these could be measured, followed approximately the same M-bulge relation observed in the local universe. The expectations for JWST were, by every careful description, that the same general types of objects would be observed at higher redshifts and in greater detail. JWST would see more of them, it would see fainter ones, it would see them at earlier cosmic epochs. But it would see, by every careful estimate, essentially the same kinds of objects, extended further back into cosmic history. That expectation was, by every careful description, wrong. JWST did find the expected extended galaxies. It found them in much greater numbers than Hubble had been able to detect. It found them at higher redshifts and at fainter magnitudes. But JWST also found something that Hubble had completely missed. JWST found, in the early extragalactic surveys, a substantial population of compact, very red objects that did not match any expected category. The objects were called, almost immediately after their identification, the little red dots. The first systematic identification of the little red dots was reported by Dale Kocevski at Colby College and his collaborators in a paper published in 2023. The Kocevski paper analyzed the early JWST CEERS survey data and identified a population of objects that were unusually compact and unusually red compared to all previously known classes of high redshift sources. The discovery was followed almost immediately by additional reports from other research groups using other JWST surveys. Rebecca Larson at the Rochester Institute of Technology reported similar objects in the JWST JADES survey. Matthee at the Institute of Science and Technology Austria reported them in a separate survey program. Roberto Maiolino at the University of Cambridge reported them in the GA9FES program. The total catalogue of little red dots from the early JWST observations grew, by every careful estimate, from a handful to dozens to hundreds to thousands over the course of just a year. The objects were everywhere in the JWST data, but they had been invisible to Hubble. The detailed observational properties of the little red dots are, by every careful description, what makes them strange. They are extremely compact. The objects show as point sources at the JWST resolution limit with intrinsic sizes that must be smaller than approximately 100 parsecs. In comparison, a typical high redshift galaxy has a size of a few kiloparsecs. The little red dots are, by every careful estimate, at least 10 times more compact than typical high redshift galaxies. They are extremely red. The objects have spectra that show substantial flux at long wavelengths and much less flux at short wavelengths. The red colors are, in the initial interpretations, attributed to dust obscuration. But the dust interpretation, as we will discuss in detail later tonight, runs into specific problems that the JWST follow-up observations have made increasingly difficult to ignore. They show broad emission lines characteristic of accretion onto a central black hole. The broad emission lines have widths of approximately 1,000 to several thousand kilometers per second, characteristic of high-velocity gas orbiting close to a massive black hole. The black hole masses inferred from the broad emission line widths are, by every careful estimate, approximately 1 million to 100 million solar masses. The masses are large by every careful description compared to the visible mass of the surrounding structure. They are numerous. The total catalogue of little red dots from JWST observations is now in the thousands and growing. The objects are not rare curiosities. They are a substantial population of objects. in the early universe. The cumulative effect of all these properties is, by every careful description, that the little red dots do not fit any of the standard categories of astronomical objects. They are not normal galaxies, the masses are too small and the sizes are too compact. They are not normal quasars. The luminosities are too low and the host structures are too small. They are not normal, compact, star-forming regions. The emission line widths are too broad and the central masses are too large. They are something else. But what? That question is, by every careful description, what we will spend the rest of tonight answering. The initial interpretation of the little red dots was, by every careful description, the most straightforward one. The objects were red. Dust makes things red. Therefore, the objects were probably dust obscured. The interpretation was in early 2023, the consensus working hypothesis. But the dust interpretation has run into specific observational problems that have, by every careful estimate, made it increasingly difficult to maintain. Let's walk through those problems carefully, because they are central to why the black hole star interpretation has emerged as the leading alternative. The first problem with the dust interpretation is the lack of mid-infrared emission. Dust absorbs short wavelength light. It then re-emits the absorbed energy at longer wavelengths, primarily in the mid-infrared range. A dust-obscured object should, by every careful prediction, show substantial emission in the mid-infrared as the absorbed energy is re-radiated. The little red dots have been observed in the mid-infrared with JWST's MIRI instrument and with the Spitzer Space Telescope archive data. But the mid-infrared emission, by every careful measurement, is much weaker than the dust interpretation predicts. The objects are not re-emitting in the mid-infrared at the levels they should be if the redness came from dust absorption. The discrepancy is, by every careful estimate, substantial. Some little red dots have mid-infrared fluxes that are factors of 10 or more below what the dust models predict. The second problem is the spectral shape. Dust absorption produces a specific spectral curve. The curve has a characteristic shape that depends on the size distribution of the dust grains and their chemical composition. The shape has been measured in many dust-obscured objects in the local universe and at moderate redshifts. The little red dot spectra have shapes that, by every careful comparison, do not match the standard dust absorption curves. The discrepancy was first pointed out in detail by Jenny Green at Princeton University and her collaborators in papers published in 2024. But subsequent papers from various other research groups have confirmed the discrepancy in increasing detail. The little red dot spectra look red. They do not look dust-reddened in the way that dust-obscured objects in the local universe look red. The third problem is the lack of polarization. Dust grains, when they absorb and scatter light, produce specific polarization signatures. The signatures depend on the orientation of the grains and the geometry of the dust distribution. The little red dots have been observed with polarimetric instruments by various research groups. But the polarization signatures, by every careful measurement, are not what dust would produce. The objects either have very low polarization or have polarization patterns that do not match the dust models. The fourth problem is the variability behavior. Dust-obscured objects vary in specific ways as the obscuring dust moves around in front of the source. The variability has characteristic timescales and amplitudes. The little red dots, where variability has been measured, show variability patterns that do not match the dust models. Several teams have monitored individual little red dots over months to years. The variability is, by every careful description, consistent with intrinsic variability of the central source rather than with dust obscuration changes. The fifth problem is the inferred dust column densities. If the redness of the little red dots came from dust, the implied dust column densities would have to be, by every careful estimate, extremely high. The column densities would correspond to, in some cases, more dust per unit area than is observed in any local universe galaxy. The high dust columns would in turn require very efficient dust production in the early universe. But the standard models of dust production in early galaxies cannot, by every careful estimate, produce the required amounts of dust on the available cosmic timescales. The dust interpretation requires either modifications to dust production physics or a substantial enrichment from very early stellar generations that current models do not predict. The cumulative effect of all these problems is, by every careful description, that the simple dust interpretation has become increasingly difficult to maintain. Many research groups have, over the past 2 years, moved away from the dust interpretation toward alternative explanations. But the dust interpretation has not been completely abandoned. Some research groups continue to argue that modified dust models can match the observations. The detailed parameters required for the modified models are, by every careful estimate, extreme. The dust would have to have, in some scenarios, very unusual properties not observed in any local universe dust. The dust would have to be distributed in specific geometric configurations to match the observed colors without producing the expected mid-infrared emission. The modifications are, by every careful description, possible but increasingly contrived. The shift away from the dust interpretation has, by every careful estimate, opened the theoretical space for alternative interpretations. The leading alternative, as we will discuss in the next sections of our conversation tonight, is the black hole star framework. The framework explains the observed colors through a completely different physical process. It does not require dust at all. The redness comes, in the framework, from the properties of the radiation-supported gas envelope that surrounds the central, accreting black hole. But before we get to the black hole star framework, let's look at one more piece of evidence that has, by every careful estimate, pushed the field toward the alternative interpretation. The evidence is the structure of the little red dot spectra at specific emission lines and what those lines reveal about the conditions of the gas producing them. Let's spend more time on the compactness of the little red dots, because the compactness is, by every careful description, one of the most striking features of the observations. The objects appear in the JWST images as point sources. The point source nature is, by every careful estimate, the first observational signature that distinguishes the little red dots from normal high redshift galaxies. Tonight, we will work through exactly what the compactness tells us about the physical structure of the objects. The JWST has a specific angular resolution that depends on the wavelength of observation. At the shortest wavelengths, JWST achieves angular resolutions of approximately 0.05 arcseconds. At longer wavelengths, the resolution is somewhat worse. The angular resolution corresponds to specific physical sizes at high redshifts. At a redshift of 5, 1 arcsecond corresponds to approximately 6 kiloparsecs. At a redshift of 7, 1 arcsecond corresponds to approximately 5 kiloparsecs. The angular resolution of JWST corresponds to physical resolutions of approximately 1/4 to 1/3 of a kiloparsec at the relevant redshifts. A typical high redshift galaxy has a physical size of a few kiloparsecs. The galaxy is, in this sense, easily resolved by JWST observations. The galaxy appears as an extended structure with measurable size. But the little red dots do not appear as extended structures. They appear, by every careful description, as point sources at the JWST resolution limit. The point source nature means that the intrinsic size of each little red dot must be smaller than approximately 300 parsecs. The constraint is, by every careful estimate, much smaller than the size of any normal high redshift galaxy. The little red dots are, in this sense, at least 10 times more compact than typical high redshift galaxies. The compactness constraint has been refined through specific observations that push the angular resolution beyond the standard JWST resolution. The technique involves observations of strongly lensed little red dots, where gravitational lensing by foreground galaxies provides additional magnification. The strongly lensed objects can be observed at effective resolutions of approximately 10 to 100 parsecs. The detailed observations have, by every careful estimate, constrained the intrinsic sizes of several little red dots to be smaller than approximately 10 parsecs. The constraint is, by every careful description, extraordinarily tight. 10 parsecs is approximately the size of a small star cluster or a very dense region of a normal galaxy. The little red dots are, by every careful estimate, that compact or smaller. The detailed implications of the compactness for the physical structure are, by every careful description, substantial. The compact structure cannot, by every careful estimate, be a normal galaxy. A galaxy that's small with the observed luminosities would have to be extraordinarily dense, with stellar densities orders of magnitude above any observed galaxy. The compact structure cannot, by every careful estimate, be a normal star cluster. A star cluster with the observed broad emission lines would have to have specific dynamical properties that are not consistent with the observed line widths. The compact structure cannot, by every careful estimate, be a normal compact starburst region. The luminosities and emission line properties are not consistent with the standard compact starburst models. The compact structure must be, by every careful description, something else. The black hole star framework provides a natural explanation for the compactness. The envelope of the black hole star has a size of approximately astronomical units to perhaps thousands of astronomical units. The size is, by every careful estimate, far below the resolution of any current or planned telescope. The object appears as a point source from any practical observation distance. The compactness is, by every careful description, a natural consequence of the framework structure. But the alternative interpretations have, by every careful estimate, more difficulty explaining the compactness. The modified dust interpretation requires the dust to be distributed in very compact geometries that are not natural in normal astrophysical environments. The compact starburst interpretation requires the starburst region to be extraordinarily compact compared to any observed starburst. The dense star cluster interpretation requires the cluster to be extraordinarily dense compared to any observed cluster. The detailed comparisons favor, by every careful estimate, the black hole star framework as the most natural explanation for the compactness. The compactness constraints continue to be refined as additional observations accumulate. The strongly lensed little red dots provide, by every careful description, the tightest constraints. The continuing search for additional strongly lensed examples is, by every careful estimate, an active area of investigation. The detailed lens modeling that allows the compactness constraints to be extracted from the observations is, by every careful description, computationally intensive, but achievable. The constraints will, by every careful estimate, continue to improve as more strongly lensed examples are identified and as the lens modeling becomes more sophisticated. The future observations with the next-generation telescopes will, by every careful description, push the compactness constraints to even tighter limits. The extremely large telescope, when operational in 2028, will have angular resolution approximately 5 times better than JWST. The combined ELT and strong lensing observations will, by every careful estimate, allow constraints on the intrinsic sizes at the level of a few parsecs or less. The detailed constraints will, by every careful description, definitively distinguish the various theoretical interpretations of the little red dots. The compactness is, by every careful description, one of the strongest pieces of observational evidence for the black hole star framework. The framework predicts the compactness as a natural consequence of the envelope structure. The alternatives require special configurations to match the observed compactness. The framework is, by every careful estimate, the most natural explanation for the observed sizes. Let's look at the emission line spectroscopy of the little red dots in detail. The emission lines are, by every careful description, where the most striking evidence for the unusual nature of these objects comes from. The standard expectation for compact accreting objects is that they would show specific emission line patterns characteristic of the conditions in the accretion disk and the surrounding broadline region. The patterns have been observed in thousands of quasars and active galactic nuclei across the universe. The little red dots show broad emission lines. The lines have widths of approximately 1,000 to several thousand kilometers per second. The widths are characteristic of high-velocity gas orbiting close to a central massive black hole. The widths allow estimates of the central black hole mass through the standard scaling relations developed for normal quasars and active galactic nuclei. But the broad emission lines in the little red dots are in detailed properties different from the broad emission lines in normal quasars. The differences are subtle, but, by every careful measurement, real. The first difference is in the line ratios. The relative strengths of different emission lines depend on the physical conditions of the emitting gas. The temperature, the density, the ionization level, and the chemical composition all affect the line ratios. The line ratios in the little red dots are, by every careful measurement, different from the line ratios in normal quasars at the same redshifts. The differences suggest that the gas conditions in the little red dot broadline regions are different from the gas conditions in normal quasar broadline regions. The detailed interpretation of the line ratio differences is, by every careful description, still being worked out. But the differences are real and consistent across the little red dot population. The second difference is in the line profiles. The shapes of the broad emission lines provide information about the geometry and dynamics of the emitting gas. The shapes have been measured in detail for individual little red dots through high-resolution spectroscopy. The shapes show, by every careful measurement, specific asymmetries and structures that differ from the typical quasar broadline profiles. Some little red dots show absorption features within the broad emission lines, suggesting that some of the emitting gas is being absorbed by gas at lower velocities along the line of sight. The absorption features are not seen in normal quasars at comparable redshifts. They suggest that the geometry of the gas around the little red dot central engines is different from the geometry around normal quasar central engines. The third difference is in the narrow emission lines. The narrow emission lines come from gas at larger distances from the central accreting object, typically several kiloparsecs away in normal galaxies. The narrow lines are sensitive to the conditions in the surrounding host galaxy. The little red dots show narrow emission lines that are, by every careful measurement, very weak or completely absent. The absence of narrow emission lines is, by every careful description, one of the most striking features of the little red dot spectra. The interpretation of the missing narrow lines is, by every careful estimate, that the surrounding host structure is either very small or has very low gas density. The host is not, by every careful description, behaving like a normal galaxy. The fourth difference is in the continuum spectral energy distribution. The continuum emission from a normal quasar comes from the accretion disk, with a characteristic blackbody-like spectrum that peaks at ultraviolet wavelengths and extends into the optical and X-ray ranges. The little red dots show continuum spectra that, by every careful measurement, differ from the standard accretion disk shape. The differences are most pronounced in the ultraviolet. The objects show much less ultraviolet flux than the standard accretion disk models would predict. The interpretation of the missing ultraviolet flux is, by every careful estimate, that the central accretion disk is somehow being shielded or modified by the surrounding gas envelope. The fifth difference is in the X-ray emission. Normal quasars produce substantial X-ray emission from hot gas in the accretion disk corona. The X-ray emission has been measured for some of the brighter little red dots using deep observations with the Chandra X-ray Observatory and the XMM Newton Observatory. The measurements show, by every careful estimate, that the little red dots produce much less X-ray emission than the standard accretion models would predict for their inferred black hole masses. The discrepancy is, by every careful description, substantial. Some little red dots have X-ray fluxes that are factors of 100 below what the standard models predict. The interpretation of the missing X-ray flux is, by every careful estimate, that the X-ray emitting corona is either absent or being absorbed by the surrounding gas envelope. The cumulative effect of all these spectroscopic differences is, by every careful description, that the little red dot emission line spectra are consistent with accretion onto a central massive black hole. But the accretion is happening in an environment that is, by every careful estimate, very different from the environment around normal quasars and active galactic nuclei. The central black hole appears to be surrounded by a substantial envelope of gas that affects the radiation in specific ways. The envelope absorbs the ultraviolet flux from the accretion disk. The envelope shields the X-ray emitting corona. The envelope modifies the broad emission line profiles. The envelope suppresses the narrow emission lines by limiting the gas at larger distances from the central source, but the envelope still allows the broad emission lines to be observed, with modifications that distinguish the little red dot spectra from normal quasar spectra. The structure of the envelope is, by every careful description, what we need to understand to interpret the little red dot observations. The black hole star framework, which we will discuss in the next section of our conversation tonight, provides a specific physical model for the envelope. The framework predicts the specific structure that, by every careful estimate, matches the observed spectral properties. Let's now look at the black hole star framework in detail. The framework was developed primarily by Mitchell Begelman at the University of Colorado, with substantial subsequent contributions from various other research groups. The framework was first proposed in papers published starting around 2010. well before the JWST observations of the little red dots had even been imagined. The original purpose of the framework was, by every careful description, different from its current application. Beagleman was working on the broader problem of how the first supermassive black holes could form in the early universe. The work was theoretical, motivated by the problem of how to grow black holes from initial seeds to the masses observed in the highest redshift quasars then known. But the framework that emerged turned out, by every careful estimate, to predict objects that match the JWST little red dots remarkably well. The basic concept of the black hole star framework is, by every careful description, straightforward. A massive black hole accreting at rates near or above the Eddington limit produces enormous amounts of radiation from the inner accretion disk. The radiation exerts outward pressure on the surrounding gas. If the gas supply is sufficiently large, the gas cannot be completely blown away by the radiation pressure. Instead, the gas forms a quasi-stable envelope around the central black hole, supported against gravity by the radiation pressure from the central accretion. The envelope is, in its structure, similar to the envelope of a massive star, with radiation pressure providing the support against the central gravity. But the central source of the radiation is, by every careful description, not nuclear fusion. It is accretion onto a central black hole. The object is, in this sense, a black hole star. The detailed physics of the envelope structure was worked out by Beagleman in subsequent papers, with collaborators including Martha Volonteri at the Institut d'Astrophysique de Paris, Eric Quatert at Princeton University, and various others. The structure has specific properties that can be calculated from the basic physical principles. The envelope has a characteristic size that depends on the central black hole mass and the accretion rate. The size is approximately 10 to 100 astronomical units for moderate mass envelopes and can extend much larger for the most extreme cases. The envelope has a characteristic temperature that depends on the radiation flux from the central accretion. The temperature is approximately 10,000 to a few tens of thousands of Kelvin, much cooler than the inner accretion disk. The envelope produces emission with a specific spectral shape. The shape is dominated by the photosphere of the envelope, the region where the optical depth becomes unity and the radiation can escape. The photospheric emission has a shape that is, by every careful estimate, different from the standard accretion disk emission. It looks more like the emission from a hot star than like the emission from a normal quasar. The difference between the predicted black hole star spectrum and the predicted standard quasar spectrum is, by every careful description, exactly the kind of difference that distinguishes the little red dots from normal high redshift quasars. The black hole star framework predicts compact appearance. The envelope is, even in its most extreme form, only astronomical units to perhaps light years in size. The angular size at high redshifts is, by every careful estimate, far below the resolution of any current telescope. The object appears as a point source. The framework predicts the absence of mid-infrared emission. The envelope is hot enough that its emission peaks in the optical and near-infrared. There is no separate cool dust component to produce mid-infrared excess. The mid-infrared flux predicted by the framework is, by every careful estimate, consistent with the low mid-infrared fluxes actually observed in the little red dots. The framework predicts the modified broad emission line properties. The broad emission lines come from gas at the inner edge of the envelope, where conditions allow the production of broad, permitted lines. but the conditions are, by every careful description, modified by the surrounding envelope structure. The detailed predictions for the line profiles, line ratios, and continuum emission match by every careful estimate the observed properties of the little red dots reasonably well. The framework predicts the suppression of narrow emission lines. The narrow emission lines normally come from gas at large distances from the central source in the surrounding host galaxy. The black hole star framework predicts that the central object is, by every careful description, not embedded in a normal galaxy at all. The central object is a black hole accreting from a pristine or near pristine gas reservoir, without the surrounding extended gas structure that would produce narrow emission lines. The prediction matches, by every careful estimate, the observed absence of narrow emission lines in the little red dot spectra. The framework predicts the suppression of X-ray emission. The central accretion disk corona, which normally produces the X-ray emission in quasars, is shielded by the surrounding envelope. The X-rays produced by the corona are absorbed before they can escape to the observer. The prediction matches, by every careful estimate, the observed low X-ray fluxes in the little red dots. The cumulative match between the predictions of the black hole star framework and the observed properties of the little red dots is, by every careful description, what has driven the field toward the black hole star interpretation over the past 2 years. The match is not perfect. There are specific properties that the framework does not yet explain in detail, but the overall agreement is, by every careful estimate, substantially better than the agreement of any alternative interpretation. The framework has, in this sense, emerged as the leading candidate for explaining what the little red dots actually are. The next sections of our conversation tonight will explore the detailed physics of the black hole star envelope in more depth and look at the specific extensions of the framework that have been developed in response to the JWST observations. Let's now look at the detailed physics of the black hole star envelope. The envelope is, by every careful description, where most of the interesting physics happens. The central black hole and its inner accretion disk are, in terms of physical scale, very small. The envelope extends to scales that are, by every careful estimate, millions of times larger than the central engine. The envelope is what we actually see when we look at a little red dot. Understanding its structure is, by every careful description, central to understanding what the objects actually are. The envelope structure starts at the inner edge near the central accretion disk. The inner edge is, by every careful estimate, at a distance of approximately tens to hundreds of gravitational radii from the central black hole. At this distance, the gas is moving at substantial fractions of the speed of light. The gas is, by every careful description, hot and highly ionized. The conditions are similar to the conditions in the broad line region of a normal quasar. But the gas at the inner edge of the envelope does not, by every careful estimate, extend outward freely as it would in a normal quasar. The gas is constrained by the surrounding envelope structure, which limits how far the broad line gas can extend and modifies the conditions in subtle ways. The envelope extends outward from the inner edge over a substantial range of distances. The detailed structure depends on the central accretion rate and the gas supply from the surrounding environment. At intermediate distances, the envelope has properties similar to the atmosphere of a hot star. The gas is dense enough to be optically thick to the radiation from the central accretion. The radiation pressure on the gas balances the gravitational attraction from the central black hole. The balance produces, by every careful estimate, a quasi-stable equilibrium that can be maintained as long as the central accretion continues, but the equilibrium is not, by every careful description, perfectly stable. The envelope can be perturbed by changes in the central accretion rate. It can be modified by the inflow of additional gas from the surrounding environment. It can be disturbed by various instabilities that grow and decay on specific timescales. The detailed time evolution of the envelope is, by every careful estimate, complex and an active area of theoretical investigation. The outer edge of the envelope is where the gas density becomes low enough that the radiation can escape freely. The outer edge is, in the typical models, at a distance of approximately astronomical units, to perhaps thousands of astronomical units from the central black hole. The exact distance depends sensitively on the central accretion rate. The outer edge is what determines the photospheric properties of the envelope, the effective temperature and radius that determine the spectral energy distribution observed by distant observers. The photospheric properties have been calculated in detail by various research groups. The calculations use radiative transfer codes that solve for the propagation of the radiation through the gas envelope. The codes include detailed treatment of the gas opacities, the radiation pressure forces, and the dynamics of the gas flow. The calculations are computationally intensive and require, by every careful estimate, substantial supercomputer resources. The current state of the calculations is, by every careful description, advanced. Various research groups have produced detailed models that can be compared directly to the observed spectra of individual little red dots. The match between the models and the observations is, by every careful estimate, encouraging. But the match is not perfect. There are specific features in the observed spectra that the current models do not reproduce in detail. The detailed differences are, by every careful description, what current theoretical work is trying to address. The structure of the envelope determines specific observational predictions that have been tested against the JWST data. The first prediction is the spectral energy distribution. The predicted shape matches, by every careful estimate, the observed shape of the little red dot spectra. The match is not exact, but it is substantially better than the match of any standard accretion disk model. The second prediction is the variability behavior. The envelope can vary on specific timescales as the central accretion rate changes or as the gas supply changes. The predicted variability timescales are, by every careful estimate, approximately months to years for the photospheric variability. The observed variability of individual little red dots, where it has been measured, is consistent with these predicted timescales. The third prediction is the emission line behavior. The broad emission lines come from gas near the inner edge of the envelope. The detailed line profiles and ratios depend on the conditions at the inner edge, which are modified by the surrounding envelope structure. The predicted line properties match, by every careful estimate, the observed properties of the little red dot emission lines reasonably well. The fourth prediction is the polarization behavior. The envelope geometry produces specific polarization signatures that depend on the orientation of the envelope relative to the observer. The predicted polarization is, by every careful estimate, low for the spherical or near-spherical envelope geometries that are favored by the current models. The observed polarization of the little red dots is, by every careful description, consistent with the low polarization prediction. The cumulative match between the envelope physics predictions and the observed properties of the little red dots is, by every careful estimate, substantial. But the match is not yet complete. There are specific aspects of the observed spectra that require additional theoretical work to fully understand. The detailed shape of the spectrum at specific wavelengths, the precise widths and asymmetries of individual emission lines, and the detailed variability patterns are all aspects where the current models are still being refined. The work is, by every honest description, in active development. The framework continues to be extended and refined as more observations accumulate. Let's now look at the question of how long a black hole star can exist. The lifetime question is, by every careful description, central to understanding why the little red dots are observed in the early universe and not in the local universe. The lifetime depends on specific physical conditions that prevail only in particular cosmic environments. Tonight, we will work through the detailed lifetime calculation and what it tells us about the cosmic epoch of black hole star formation. The lifetime of a black hole star depends on three specific factors. The first is the gas supply from the surrounding environment. The envelope requires continuous gas inflow to maintain its mass against the radiation-driven outflows and the central accretion. If the gas supply is exhausted, the envelope dissipates. The second is the central accretion rate. The accretion rate determines the radiation flux that supports the envelope structure. If the accretion rate drops below a critical threshold, the radiation pressure becomes insufficient to support the envelope, and the envelope collapses or dissipates. The third is the stability of the envelope structure itself. The envelope can be perturbed by various instabilities that grow on specific timescales. If the instabilities become sufficiently severe, the envelope is disrupted even if the gas supply and accretion rate are maintained. The detailed lifetime calculations have been performed by various research groups. The calculations include detailed treatment of all three factors. The current best estimates are that black hole star lifetimes are, by every careful description, approximately 10 million to 100 million years for typical conditions. The lifetimes are short compared to cosmic timescales, but long compared to many other astrophysical timescales. The lifetimes are sufficient, by every careful estimate, for the black hole stars to be observed during a substantial fraction of the relevant cosmic epoch. But the lifetimes are not, by every careful description, infinite. The black hole stars eventually dissipate as the conditions change. The cosmic conditions that allow black hole star formation are, by every careful description, specific. The formation requires direct collapse black hole seeds, which form preferentially in pristine gas environments during the very early universe. The growth requires continuous gas supply from the surrounding environment. The envelope formation requires the accretion rate to reach the threshold at which the radiation pressure can support a quasi-stable gas structure. The conditions are all most easily satisfied during the first few 100 million to 1 billion years of cosmic history. After that, the conditions change. The gas becomes more chemically enriched, reducing the efficiency of direct collapse seed formation. The cosmic structure develops with the formation of normal galaxies that disrupt the conditions for envelope support. The central black holes either grow to masses that exceed the threshold for envelope formation or transition to more conventional accretion modes. The cosmic environment becomes, by every careful estimate, increasingly hostile to the maintenance of black hole star structures. The little red dots are, in this picture, observations of a cosmic phenomenon that operated during a specific, limited cosmic epoch. The phenomenon was, by every careful description, characteristic of the early universe, but not characteristic of the local universe. The detailed redshift distribution of the observed little red dots provide strong constraints on the timing of the phenomenon. The current best estimates from the JWST observations are that the little red dot population peaks at redshifts of approximately 5 to 7, corresponding to cosmic ages of approximately 700 million to 1 billion years after the Big Bang. The population declines at higher and lower redshifts. At higher redshifts, the cosmic age is too short for sufficient black hole seed growth. At lower redshifts, the cosmic conditions have changed sufficiently that envelope formation is less common. The detailed shape of the redshift distribution matches, by every careful estimate, the predicted distribution from the black hole star framework reasonably well, but the match is not yet, by every careful description, perfect. The detailed quantitative comparison is still being refined as more observations accumulate. The continuing observations will, by every careful estimate, substantially refine the redshift distribution measurements. The implications for the broader cosmic history are, by every careful description, substantial. The black hole stars are not just curious individual objects, they are evidence for a specific cosmic phase that operated in the early universe and produced a substantial population of objects that subsequently evolved into more conventional active galactic nuclei or dormant supermassive black holes. The detailed evolutionary tracks from black hole stars to mature, supermassive black holes are, by every careful estimate, still being worked out, but the broad outlines are now reasonably clear. The black hole stars are, in this picture, the missing link between the direct collapse seed formation in the very early universe and the mature, supermassive black holes observed at all cosmic epochs. The connection between the little red dots and the broader cosmic structure formation is, by every careful description, a particularly important aspect of the framework. The little red dots are, by every careful estimate, observed in the same cosmic epoch when the first galaxies are forming and the first generations of stars are completing their evolution. The development of the cosmic structure is, by every careful description, intimately connected with the formation and evolution of the central supermassive black holes. The little red dots provide, by every careful estimate, direct observational evidence for the central role that the supermassive black holes played in this early cosmic structure formation. The detailed implications continue to be worked out by ongoing research. Let's now consider what makes the black hole star interpretation, by every careful description, strange. The strangeness is not just a matter of unfamiliarity. It is, by every careful estimate, a substantive aspect of the framework that deserves to be examined directly. The little red dots, if the black hole star interpretation is correct, are a class of objects that does not exist in the local universe at all. They are not just early versions of objects that we see locally. They are something fundamentally different that the universe used to make and no longer makes. Tonight, we will look at exactly why that is. The first aspect of the strangeness is the size scale of the central object. A normal star has a size of, at most, a few thousand times the radius of the Sun. The Sun's radius is approximately 700,000 kilometers, so a normal star has a size of, at most, a few billion kilometers, or roughly the size of the orbit of the outer planets in the solar system. A black hole star, by every careful estimate, has a size that can extend to thousands of astronomical units. 1 astronomical unit is the distance from the Earth to the Sun, approximately 150 million kilometers. 1,000 astronomical units is, by every careful description, far larger than any normal star. The size of a black hole star is comparable to the size of the solar system itself, but with the central engine being not a star, but a million solar mass black hole. The scale is, by every careful description, unlike anything else in modern astrophysics. The second aspect of the strangeness is the energy source. A normal star is powered by nuclear fusion in the core. The fusion produces, over the lifetime of the star, approximately 1 billion times the rest mass energy of the fuel that is consumed. The energy is, by every careful description, enormous but finite. A black hole star is powered by gravitational accretion onto the central black hole. The accretion is, by every careful estimate, far more efficient than nuclear fusion. The standard 10% efficiency of accretion is approximately 100 times more efficient than the standard 0.7% efficiency of nuclear fusion. But the accretion is not, by every careful description, limited in the same way that nuclear fusion is. A normal star runs out of fuel and dies. A black hole star can, in principle, continue accreting as long as gas is supplied to the central region. The lifetime of a black hole star depends on the gas supply, not on a fixed fuel reserve. The third aspect of the strangeness is the chemical composition. A normal star has a chemical composition that reflects the composition of the gas from which it formed. The composition is, by every careful estimate, approximately the composition of the surrounding interstellar medium at the time of star formation. A black hole star, by every careful description, has a chemical composition that reflects the accretion history of the central black hole. The composition is, in the early universe, expected to be primarily hydrogen and helium, with very small amounts of heavier elements. The gas around the central black hole is pristine or near pristine, having not yet been enriched by multiple generations of stellar nucleosynthesis. The chemical composition is, by every careful description, different from any normal star in the local universe. The fourth aspect of the strangeness is the eventual fate. A normal star eventually exhausts its nuclear fuel and either becomes a compact remnant, a neutron star, or a stellar mass black hole, depending on the initial mass. The remnant is, by every careful description, a specific and well-understood endpoint of stellar evolution. A black hole star does not have, by every careful estimate, a clear endpoint. The central black hole continues to grow as long as gas is accreted. The envelope continues to be supported as long as the accretion produces sufficient radiation. The eventual evolution depends on the gas supply from the surrounding environment. If the gas supply is exhausted, the envelope eventually dissipates and the central black hole becomes a normal, accreting object. If the gas supply continues, the central black hole can grow to enormous masses while remaining surrounded by the envelope structure. The detailed evolution is, by every careful description, not yet fully understood, but the framework predicts, by every careful estimate, that black hole stars are a transient phenomenon in cosmic history. They exist for the limited cosmic epoch during which their specific formation conditions prevail. The fifth aspect of the strangeness is the connection to the surrounding cosmic structure. A normal star is embedded in a galaxy, which is embedded in a galaxy cluster, which is embedded in a larger cosmic web of galaxy filaments. The star is, by every careful description, part of a hierarchical cosmic structure. A black hole star, by every careful estimate, is not embedded in a normal galaxy at all. The host structure around a black hole star is, in the current models, very small. The central black hole is the dominant component of the system. The visible structure is, by every careful description, just the central object plus its surrounding envelope, with no surrounding extended galactic structure. The black hole star is, in this sense, an isolated cosmic object rather than a galactic component. The cumulative effect of all these strange aspects is, by every careful description, that the black hole stars are a fundamentally new class of cosmic object. They are not familiar objects in unfamiliar conditions. They are something that the universe used to make through specific physical processes that no longer operate. The little red dots are, in the black hole star interpretation, the only direct observational evidence we have for this class of objects. The cosmic epoch during which they existed is, by every careful estimate, limited to approximately the first few 100 million to 1 billion years after the Big Bang. Before that, the conditions for forming direct, collapse black hole seeds were not yet established. After that, the gas supply was sufficiently disrupted by the developing cosmic structure that the envelope formation became impossible. The little red dots are, by every careful description, observations of a specific cosmic phenomenon that operated only briefly in cosmic history. The strangeness of the interpretation is, by every careful estimate, exactly what makes it scientifically important. Let's now look at the specific extensions of the black hole star framework developed in response to the JWST observations. The original Begelman framework, developed in the early 2010s, was a general theoretical proposal that did not have specific observational targets to match. The JWST observations of the little red dots provided, by every careful description, the first concrete observational test of the framework. The extensions have, by every careful estimate, been developed primarily by Kohei Inayoshi at Peking University and Roberto Maiolino at the University of Cambridge, with substantial contributions from various other research groups. The Inayoshi extensions of the framework focus on the detailed properties of the central accretion. The original Begelman framework treated the central accretion in a relatively simplified way, focusing on the average properties of the radiation pressure support of the surrounding envelope. The Inayoshi extensions add detailed treatment of the accretion physics, including the specific structure of the inner accretion disk, the production of the broad line region, and the connection between the central engine and the surrounding envelope. The extensions allow more detailed predictions for specific observational features. The predictions can be compared directly to the observed spectra of individual little red dots. The match is, by every careful estimate, encouraging, but the match is not yet perfect for any individual object. There are specific features in the observed spectra that the current models do not reproduce in detail. The Maiolino extensions of the framework focus on the connection between the black hole star and the surrounding cosmic environment. The original Begelman framework treated the surrounding environment in a relatively simplified way, primarily as a gas reservoir that could supply the central accretion. The Maiolino extensions add detailed treatment of the cosmological context, including the formation of the central black hole seed through direct collapse, the growth of the seed through accretion from the surrounding gas, the development of the envelope structure as the accretion rate increases, and the eventual transition to a more conventional active galactic nucleus as the gas supply changes. The extensions provide, by every careful description, a complete cosmic biography of the black hole star phenomenon. The biography starts with the direct collapse seed formation in the very early universe. The seed grows rapidly through accretion from the surrounding pristine gas. The accretion produces, at some point in the growth process, sufficient radiation to support a quasi-stable envelope of gas. The envelope structure is, by every careful estimate, what we observe as a little red dot. The envelope persists for the cosmic epoch during which the conditions for envelope support are maintained. Eventually, the gas supply changes, the envelope dissipates, and the central black hole becomes a more conventional active galactic nucleus, or a dormant black hole. The detailed timing of these phases varies by every careful estimate from individual object to individual object. The detailed observational predictions of the Majorino extensions have been worked out in detail. The predictions include specific patterns for how the little red dot population should evolve across cosmic time. The predictions can be tested against the JWST observations of little red dots at different redshifts. The current best estimates are that the little red dot population peaks at redshifts of approximately 5 to 7, corresponding to cosmic ages of approximately 700 million to a billion years after the Big Bang. The population declines by every careful estimate at lower redshifts as the conditions for envelope support become less common. The observed redshift distribution of little red dots from JWST surveys matches, by every careful description, the predicted distribution reasonably well. The match is one of the strongest pieces of evidence for the black hole star interpretation, but the match is not yet, by every careful estimate, definitive. The detailed, quantitative comparison between the predicted and observed populations is still being refined as more JWST surveys complete and as the population statistics improve. The continuing observations will, by every careful estimate, substantially refine the population-level predictions. Beyond the Inayoshi and Majorino extensions, additional theoretical work has been done by various other research groups. Andy Goulding at Princeton University has worked on the detailed connection between the black hole star envelope and the broadline region properties. The work focuses on how the inner edge of the envelope produces the observed broad emission lines. The detailed predictions for the line profiles, line ratios, and line variability have been worked out in detail. The predictions match, by every careful estimate, the observed properties reasonably well. Anna Christina Eilers at the Massachusetts Institute of Technology has worked on the connection between the little red dots and the broader population of high redshift quasars. The work focuses on how the black hole star phase fits into the overall evolutionary track from direct collapse seed to mature supermassive black hole. The detailed predictions for the cosmic abundance of objects at each evolutionary stage have been worked out. The predictions match, by every careful estimate, the available observations reasonably well. The cumulative effect of all these theoretical extensions is, by every careful description, that the black hole star framework has matured substantially over the past 2 years. The framework is no longer a general theoretical proposal. It is, by every careful estimate, a detailed theoretical model that makes specific quantitative predictions for the observed properties of the little red dots. The model can be tested in detail against the JWST data. The detailed match between the model predictions and the observed properties is, by every careful estimate, what has driven the field toward the black hole star interpretation as the leading framework. But the framework is, by every honest description, not yet definitively confirmed. There are alternative interpretations that continue to be developed. The detailed observational tests are, by every careful estimate, still in progress. The next several years of JWST observations and theoretical work will substantially refine the picture. Let's now look at the specific observational matches between the black hole star framework predictions and the JWST data. The matches are, by every careful description, what has driven the field toward the framework as the leading interpretation. The matches are not perfect for any individual observed property, but the cumulative pattern of matches across many different observational tests is, by every careful estimate, substantial. Tonight, we will work through the detailed comparison in a systematic way. The first match is in the color properties of the little red dots. The framework predicts that the photospheric emission from the envelope should produce a specific spectral shape with characteristic colors. The predicted colors have been compared to the observed colors of hundreds of little red dots. The match is, by every careful estimate, good in the optical and near-infrared wavelength ranges. The detailed shape of the spectral energy distribution between approximately 1 micron and 5 microns matches, by every careful description, the framework predictions within the observational uncertainties. But the match is not as good at shorter wavelengths. The observed ultraviolet flux is, by every careful estimate, somewhat lower than the framework predicts for some little red dots. The discrepancy is, by every careful description, an active area of investigation. The current best interpretations involve additional absorption of the ultraviolet flux by gas in the inner envelope or by gas immediately outside the envelope. The detailed mechanism is, by every careful estimate, still being worked out. The second match is in the broad emission line properties. The framework predicts that the broad emission lines come from gas at the inner edge of the envelope, where the conditions allow the production of permitted lines with specific widths and ratios. The predicted line widths match, by every careful estimate, the observed widths reasonably well. The predicted line ratios match, by every careful description, the observed ratios with some refinements needed for specific transitions. The detailed line profile shapes match, by every careful estimate, the observed shapes for some little red dots, but not all of them. The detailed differences between predictions and observations for the line profiles are, by every careful description, an active area of investigation. The third match is in the narrow emission line properties. The framework predicts that narrow emission lines should be very weak or absent, because the central object is not embedded in a normal galaxy with extended gas at large distances from the central source. The observed little red dot spectra show, by every careful measurement, very weak or completely absent narrow emission lines. The match is, by every careful estimate, excellent. The absence of narrow emission lines is, by every careful description, one of the strongest pieces of evidence for the black hole star framework. The alternative interpretations have, by every careful estimate, more difficulty explaining the absence. The fourth match is in the X-ray properties. The framework predicts that X-ray emission should be substantially suppressed compared to standard accretion models, because the X-ray emitting corona is shielded by the surrounding envelope. The observed X-ray fluxes are, by every careful measurement, substantially below the standard model predictions for the inferred black hole masses. The match is, by every careful estimate, good. The discrepancy from the standard models is, by every careful description, consistent with the envelope absorption predicted by the framework. But the detailed quantitative match requires additional refinement. The exact level of X-ray suppression varies, by every careful estimate, between individual little red dots. The variations may reflect different envelope structures for different objects. The fifth match is in the variability properties. The framework predicts specific variability timescales for the photospheric emission, the broad emission lines, and the continuum spectrum. The predicted timescales are approximately months to years for the photospheric variability and shorter for the broad emission line variability. The observed variability of individual little red dots Where it has been measured is, by every careful estimate, consistent with the predicted timescales. The match is, by every careful description, encouraging. But the detailed quantitative comparison requires, by every careful estimate, more sustained variability monitoring of larger samples of little red dots. The continuing observations will provide stronger tests. The sixth match is in the polarization properties. The framework predicts low polarization for spherical or near-spherical envelope geometries, which are favored by the current theoretical models. The observed polarization of the little red dots, where it has been measured, is, by every careful estimate, low and consistent with the framework predictions. The match is, by every careful description, encouraging but limited by the small sample of polarimetric observations to date. The cumulative match across all 6 observational properties is, by every careful estimate, substantial. The framework predicts the qualitative features of the observed spectra. It predicts the quantitative properties with reasonable accuracy. It predicts the variability and polarization behavior consistently with the available observations. The match is not perfect. There are specific features that require additional theoretical work to fully understand. But the overall pattern of matches is, by every careful description, substantially better than the pattern of matches for any alternative interpretation. The black hole star framework is, by every careful estimate, the leading candidate for explaining what the little red dots actually are. The continuing observations and theoretical work will refine the picture further. The detailed conclusions are, by every honest description, still being developed. But the current best understanding is that the little red dots are black hole stars, with all of the strange implications that the interpretation carries. Let's now consider the alternative interpretations of the little red dots that have been proposed alongside the black hole star framework. The alternatives are, by every careful description, important to consider. The black hole star framework is, by every careful estimate, the current leading candidate. But it is not the only candidate. Other research groups have proposed alternative interpretations that explain different aspects of the observations. The detailed comparison between the alternatives is, by every careful description, an active area of investigation. Tonight, we will work through the main alternatives and consider their strengths and weaknesses. The first alternative is the modified dust interpretation. As we discussed earlier tonight, the simple dust interpretation runs into specific observational problems. But various research groups have proposed modified dust models that try to address the problems. The modified models propose, by every careful estimate, very unusual dust properties not observed in any local universe dust. The dust would have to be composed of very small grains with specific chemical compositions distributed in specific geometric configurations. The modifications are, by every careful description, possible but increasingly contrived. The modified dust interpretation has, by every careful estimate, supporters in the research community but is not the leading interpretation. The second alternative is the compact starburst interpretation. The interpretation proposes that the little red dots are not accreting black holes at all. They are compact, intense starbursts in small early galaxies. The starburst interpretation explains the compactness through the small size of the host galaxy. It explains the redness through the absorption of the starburst light by surrounding gas. But the starburst interpretation has, by every careful estimate, specific problems with the observed broad emission lines. The widths of the broad lines are too large to come from gas motions in a normal starburst region. The widths require, by every careful description, gas moving at velocities characteristic of accretion onto a massive central object. The starburst interpretation has, by every careful estimate, supporters, but is not the leading interpretation either. The third alternative is the dense star cluster interpretation. The interpretation proposes that the central object is not a single supermassive black hole. It is a dense cluster of intermediate mass black holes that, collectively, produce the observed signatures. The cluster interpretation explains the broad emission lines through the combined orbital motions of the multiple black holes. But the cluster interpretation has, by every careful estimate, specific problems with the long-term stability of the proposed configurations. The dense clusters of intermediate mass black holes would, by every careful description, dynamically interact and merge on relatively short timescales. The configurations could not, by every careful estimate, persist for the cosmic epochs over which the little red dots are observed. The cluster interpretation has limited support. The fourth alternative is the modified accretion disk interpretation. The interpretation proposes that the little red dots are accreting onto a central massive black hole, but with a different accretion geometry than the standard quasar model. The modified geometry could involve, by every careful estimate, a slim accretion disk, a thick disk with extended structure, or various other variations on the standard model. The modified geometry could potentially explain some of the observed properties without invoking the full black hole star envelope. But the modified accretion disk interpretation has, by every careful estimate, specific problems with explaining the observed compactness and the suppression of X-ray emission. The compactness requires, by every careful description, very specific geometric configurations that are difficult to maintain. The X-ray suppression requires, by every careful estimate, substantial gas absorption that the simple modified disk models do not naturally provide. The modified accretion disk interpretation has, by every careful estimate, supporters but faces specific difficulties. The fifth alternative is a hybrid interpretation that combines aspects of multiple frameworks. The hybrid interpretations propose that the little red dots are a heterogeneous population, with different individual objects, best described by different combinations of the proposed mechanisms. Some little red dots might be primarily black hole stars, others might be primarily modified, dust-obscured, compact, accreting objects. Still others might be primarily compact, starbursts, with embedded accreting black holes. The hybrid interpretations are, by every careful description, attractive, because they avoid the need to identify a single mechanism that explains all of the observations. But the hybrid interpretations have, by every careful estimate, the disadvantage that they require multiple distinct mechanisms to operate simultaneously in the same cosmic environment. The hybrid interpretations are, by every careful estimate, currently under active investigation. The detailed comparison between all of these alternatives requires, by every careful description, detailed observational tests. The tests are, by every careful estimate, in progress through various ongoing JWST programs and through follow-up observations with other telescopes. The key observational tests include high-resolution spectroscopy to characterize the detailed line profiles, polarimetry to characterize the geometry of the emitting structure, variability monitoring to characterize the time evolution, multi-wavelength observations to characterize the spectral energy distribution from X-rays to mid-infrared, and statistical analysis of the population properties as a function of cosmic redshift. The cumulative tests will, by every careful estimate, eventually distinguish between the proposed alternatives. The current best estimates favor the black hole star framework as the leading single mechanism interpretation. But the alternatives are, by every careful description, still being actively investigated. The field is, in this sense, in active development. The next several years of observational and theoretical work will substantially clarify the picture. The detailed answer to what the little red dots actually are is, by every honest description, still being worked out, but the broad outlines are now reasonably clear. Let's now consider the cosmic implications of the black hole star interpretation. The implications are, by every careful description, substantial. The little red dots, if they are black hole stars, are not just curious individual objects. They are evidence for a specific cosmic process that operated in the early universe and produced a class of objects that no longer exists. Tonight, we will work through what that process tells us about how the early universe actually worked. The first implication is for our understanding of the first supermassive black holes. The little red dots provide, by every careful estimate, direct observational evidence for direct collapse black hole seed formation. The seeds, with masses of approximately 10,000 to 100,000 solar masses, formed in the very early universe through the direct collapse of pristine gas clouds. The seeds are, by every careful description, the starting point for the supermassive black holes that we observe at later cosmic epochs. The little red dots are, in this picture, the direct collapse seeds in their growth phase. They are the observational evidence that the direct collapse process actually occurred. Before the JWST observations of the little red dots, direct collapse was, by every careful description, a theoretical proposal without direct observational support. The JWST observations have, by every careful estimate, transformed direct collapse from a theoretical proposal into an observationally supported framework, but the support is not yet definitive. The detailed interpretation of the little red dots as direct collapse seeds requires the black hole star framework to be correct. If the alternative interpretations turn out to be correct, the support for direct collapse from the little red dots is, by every careful estimate, weaker. The second implication is for the cosmic timeline of supermassive black hole growth. If the little red dots are direct collapse seeds in their growth phase, the seeds are forming at cosmic ages of approximately 300 to 500 million years after the Big Bang. The seeds are growing rapidly through accretion during the first few 100 million to 1 billion years of cosmic history. The growth phase, characterized by the little red dot envelope structure, persists for the cosmic epoch during which the gas supply conditions are maintained. The eventual transition to a more conventional active galactic nucleus occurs as the gas supply changes. The cosmic timeline is, by every careful description, accelerated compared to the standard stellar seed framework. The first supermassive black holes were already forming and growing during the first few 100 million years after the Big Bang. The growth was, by every careful estimate, faster than the standard framework predicted. The eventual masses of supermassive black holes in the local universe are easier to explain in the accelerated timeline. The early supermassive black holes that JWST is observing are, by every careful description, the predictable consequence of the accelerated timeline. The third implication is for the connection between supermassive black holes and their host galaxies. The little red dots have, by every careful estimate, very small host galaxy mass relative to the central black hole mass. The mass ratio is approximately 10 to 15%, far higher than the local universe M-bulge ratio of approximately 1/10%. The little red dots are, in this sense, examples of supermassive black holes that grew before their host galaxies developed. The connection between the black holes and the galaxies in the early universe was different from the connection observed in the local universe. The black holes grew first. The galaxies caught up later. The eventual M-bulge relation was, by every careful description, established gradually as the host galaxies grew around the already massive central black holes. The fourth implication is for the chemical evolution of the early universe. The little red dots, in the black hole star interpretation, are surrounded by pristine or near-pristine gas. The gas has not yet been enriched by multiple generations of stellar nucleosynthesis. The chemical composition is, by every careful estimate, primarily hydrogen and helium, with very small amounts of heavier elements. But the chemical compositions inferred from the little red dot emission lines spectra show, by every careful measurement, substantial enrichment with heavier elements. The enrichment is, by every careful description, higher than the pristine gas interpretation would predict. The discrepancy is, by every careful estimate, an active area of investigation. Some research groups argue that the enrichment is local to the accreting region and does not reflect the broader environment. Others argue that the enrichment requires earlier generations of stellar nucleosynthesis that produced the heavy elements before the black hole accretion began. The detailed interpretation is, by every honest description, still being worked out. The fifth implication is for our understanding of the broader cosmic structure formation. The little red dots are, in the black hole star interpretation, a transient phenomenon in cosmic history. They formed during a specific cosmic epoch when the conditions for direct collapse seed formation prevailed. They evolved into more conventional active galactic nuclei as the cosmic environment developed. The transient nature of the phenomenon is, by every careful description, an example of how the early universe was producing classes of objects that no longer exist. The detailed catalogue of transient phenomena in cosmic history is, by every careful estimate, still being developed. The little red dots are, in this picture, just one example of a broader pattern. The JWST observations are revealing, by every careful description, that the early universe was a much more dynamic and diverse environment than the standard cosmological models predicted. The cumulative implications are, by every careful estimate, substantial. The little red dots are not just curious individual objects. They are observational evidence for specific cosmic processes that shaped the development of supermassive black holes, the chemical evolution of the early universe, and the broader cosmic structure formation. The detailed understanding of these implications is, by every honest description, still being developed, but the broad outlines are now reasonably clear. The next several years of observational and theoretical work will substantially refine our understanding. Let's look more carefully at the chemical composition puzzle that the little red dot observations have revealed. The puzzle is, by every careful description, one of the most striking aspects of the JWST data. It touches on questions about the broader chemical evolution of the early universe and the connection between the black hole star phenomenon and the earliest generations of stellar nucleosynthesis. The standard expectation for gas in the early universe is, by every careful estimate, that it should be primarily hydrogen and helium, with very small amounts of heavier elements. The expectation follows from the Big Bang nucleosynthesis predictions, which produce primarily hydrogen and helium, with traces of lithium during the first few minutes After the Big Bang, the subsequent enrichment with heavier elements requires multiple generations of stellar nucleosynthesis, with the heavy elements produced in stellar interiors and released into the surrounding gas through supernova explosions and stellar winds. The expected timeline for substantial chemical enrichment is, by every careful estimate, hundreds of millions of years after the Big Bang. The first generation of stars must form, evolve, and die. The released heavy elements must mix with the surrounding gas. Subsequent generations of stars must form from the enriched gas and contribute additional heavy elements. The cumulative process requires substantial cosmic time. The chemical compositions observed around the little red dots show, by every careful measurement, substantially more enrichment than the standard timeline predicts. The emission line ratios in the little red dot spectra are sensitive to the chemical composition of the emitting gas. The detailed ratios indicate, by every careful estimate, that the gas around the central engines has been enriched with heavier elements at levels that exceed the expected pristine gas composition. The discrepancy is, by every careful description, substantial. The interpretation of the chemical enrichment is, by every careful estimate, an active area of investigation. Several specific possibilities have been proposed. The first possibility is that the enrichment is local to the accreting region and does not reflect the broader gas environment. The interpretation proposes that the gas immediately around the central black hole has been enriched by specific processes operating in the accretion flow. The processes could include, by every careful estimate, accretion of stellar material from disrupted stars, accretion of supernova remnants from earlier stellar generations, or specific nucleosynthesis in the accretion disk itself. The detailed mechanisms are, by every careful description, still being worked out. The second possibility is that the enrichment requires earlier generations of stellar nucleosynthesis on accelerated timescales. The interpretation proposes that the first generation of stars formed earlier and evolved faster than the standard models predict. The accelerated stellar evolution would, by every careful estimate, produce the observed enrichment levels in the available cosmic time. But the accelerated evolution requires, by every careful description, specific stellar properties that are not characteristic of the standard models. The first generation of stars would have to be, in this interpretation, substantially more massive than the typical predictions. The third possibility is that the chemical compositions are observed in absorbing gas in front of the central engines, rather than in the gas emitting the broad emission lines. The interpretation proposes that the inferred enrichment reflects intervening gas at lower redshifts that absorbs the radiation from the central engines. The intervening gas could be, by every careful estimate, in normal galaxies along the line of sight. The interpretation would explain the observed enrichment without requiring unusual conditions in the central environments of the little red dots. But the detailed observational properties are, by every careful description, not completely consistent with simple intervening absorption. The fourth possibility is that the enrichment reflects specific nucleosynthesis processes operating in the accretion disks themselves. The interpretation proposes that the extreme conditions in the inner accretion disks of the little red dots produce heavy elements through specific nuclear reactions. The reactions could include, by every careful estimate, neutron capture processes, proton capture processes, or various other specific nucleosynthesis paths. The detailed predictions for the abundances of specific heavy elements from these processes have been worked out by various research groups. The predictions match, by every careful description, some but not all of the observed abundance patterns. The detailed work is in progress. The cumulative chemical enrichment puzzle is, by every careful estimate, one of the most active areas of current research on the little red dots. The detailed interpretation requires, by every careful description, observations that probe the chemical composition with higher precision than the current data allow. The next-generation telescopes will, by every careful estimate, provide the required precision. The ELT, GMT, and TMT will all have detailed spectroscopic capabilities that will allow precise measurements of the chemical composition of the gas around individual little red dots. The combined observations will, by every careful description, distinguish between the various interpretations of the chemical enrichment puzzle. The detailed resolution of the puzzle will, by every careful estimate, substantially refine our understanding of the broader cosmic chemical evolution. The little red dots are, in this sense, providing observational constraints not just on the formation and evolution of supermassive black holes, but on the broader chemical history of the early universe. The implications continue to be worked out. The detailed picture that is emerging from all of this work is, by every careful description, that the early universe was a much more chemically dynamic environment than the standard models predicted. The chemical enrichment was happening faster than predicted. The specific processes producing the enrichment were, by every careful estimate, different from the processes operating in the local universe. The detailed timeline of cosmic chemical evolution is, by every careful description, being substantially refined by the JWST observations and the subsequent theoretical work. Let's now look at the future observations that will refine our understanding of the little red dots and the black hole star framework. The current observational status is, by every careful description, encouraging but not definitive. The black hole star interpretation matches many of the observed properties, but specific aspects of the observations are still not fully understood. The detailed comparison between the predictions of the framework and the observed data requires, by every careful estimate, additional observations and additional theoretical work. The next several years will substantially refine the picture. The continuing JWST observations will, by every careful description, produce a substantially expanded catalogue of little red dots. The current catalogue has approximately a few thousand confirmed objects. The expanded catalogue will, by every careful estimate, reach tens of thousands of objects within the next several years. The expanded catalogue will allow detailed statistical analysis of the population properties. The redshift distribution, the luminosity distribution, the spectral property distributions, and the environmental properties can all be characterized in detail. The detailed statistical properties will, by every careful description, provide strong tests of the various theoretical interpretations. The black hole star framework predicts specific population-level properties that can be compared to the expanded catalogue. The match or mismatch will provide, by every careful estimate, definitive tests of the framework. The next-generation ground-based telescopes will, by every careful description, provide complementary observations. The extremely large telescope, currently under construction in the Atacama Desert in Chile, will have a 39-meter primary mirror, more than 5 times the size of JWST's mirror. The ELT will be capable of detecting fainter and more distant little red dots than JWST. The first ELT observations are expected in 2028. The Giant Magellan Telescope, currently under construction in Chile, will have a primary mirror equivalent to a 24.5-meter telescope. The first GMT observations are expected in the late 2020s. The 30-meter telescope currently planned for either Hawaii or the Canary Islands will have a 30-meter primary mirror. The first TMT observations are expected in the early 2030s. The combined capabilities of these next-generation telescopes will, by every careful estimate, allow detailed spectroscopic characterization of individual little red dots at higher resolution than JWST can achieve. The detailed spectroscopy will, by every careful description, reveal the specific structure of the broad emission lines, the specific properties of the surrounding gas envelope, and the specific connection between the central engine and the surrounding environment. The detailed observations will, by every careful estimate, definitively test the black hole star framework. The continuing X-ray observations with Chandra and XMM Newton, plus the future X-ray observatories Athena and Lynx, will provide complementary observations of the X-ray properties of the little red dots. The current X-ray observations are, by every careful description, limited by sensitivity. The next-generation X-ray observatories will be much more sensitive and will detect the X-ray emission from many more little red dots. The detailed X-ray properties will, by every careful estimate, provide additional tests of the black hole star framework. The framework predicts specific X-ray suppression through the surrounding envelope. The next generation X-ray observations will test the prediction in detail. The future gravitational wave observations with LISA, scheduled to launch in 2035, will provide additional observations of the early supermassive black holes. The LISA observations will detect gravitational waves from the mergers of supermassive black holes across cosmic time. The detected mergers will include, by every careful estimate, the mergers that produced the supermassive black holes that are currently being observed in their little red dot phase. The LISA observations will, by every careful description, provide direct measurements of the masses and spins of the early supermassive black holes. The measurements will test the predictions of the black hole star framework in a fundamentally different way. The framework predicts specific patterns for the spin distributions of black holes that grew through the black hole star phase. The LISA observations will, by every careful estimate, test these predictions. The continuing theoretical work will, by every careful description, refine the framework predictions. The detailed envelope structure calculations will be improved as more computational resources become available. The detailed emission line predictions will be refined as more sophisticated atomic physics calculations are incorporated. The detailed population predictions will be refined as more accurate cosmological simulations are run. The combined theoretical work will, by every careful estimate, produce increasingly detailed predictions that can be compared to the observations. The detailed comparison between the refined theoretical predictions and the refined observational data will, by every careful estimate, eventually distinguish the black hole star framework from the alternative interpretations. The cumulative future observational and theoretical work will, by every careful description, substantially clarify what the little red dots actually are. The current best understanding is, by every careful estimate, that they are black hole stars. But the understanding is, by every honest description, still being refined. The next several years will be, by every careful description, a particularly active period for this area of research. The combined observations and theoretical work will produce, by every careful estimate, definitive answers to the questions we have been discussing tonight. The detailed picture that emerges will, by every careful description, substantially refine our understanding of how the early universe produced its most extreme cosmic objects. Let's now consider in more detail what the extremely large telescope will reveal about the little red dots when it comes online in 2028. The ELT is, by every careful description, the most powerful optical and near-infrared telescope ever built. Its capabilities for studying the little red dots will, by every careful estimate, substantially exceed those of JWST in specific important ways. Tonight, we will work through what the ELT will see and what the observations will tell us about the black hole star framework. The ELT has a 39-meter primary mirror. The mirror is, by every careful description, more than 5 times the size of JWST's mirror. The larger mirror collects more light and provides higher angular resolution. The light-gathering capability is approximately 25 times that of JWST, allowing the detection of objects approximately 25 times fainter. The angular resolution at the same wavelength is approximately 5 times better, allowing physical resolutions of approximately 10 parsecs at the redshifts of the little red dots. The combined capabilities will, by every careful estimate, transform our observational understanding of the little red dots. The first ELT observations of little red dots will, by every careful description, focus on the brightest individual objects. The detailed high-resolution spectroscopy will reveal the specific properties of the broad emission lines with much higher precision than the current JWST data allow. The line profiles can be characterized in detail. The line ratios can be measured precisely. The variability of individual lines can be tracked on timescales of months to years. The detailed observations will, by every careful estimate, definitively test the black hole star framework predictions for the broad line region properties. The second area of ELT observations will be the imaging at high angular resolution. The ELT can resolve, by every careful estimate, structures of approximately 10 parsecs at the relevant redshifts. The angular resolution is, by every careful description, sufficient to characterize the immediate environments of the little red dots in detail. If the objects are embedded in compact host galaxies, the host galaxy structures should be visible. If the objects are truly isolated point sources with no surrounding extended structure, the absence of host galaxy structure will be definitively established. The detailed imaging will, by every careful estimate, distinguish between the black hole star interpretation and the alternatives that propose extended host galaxy structures. The third area of ELT observations will be the very high redshift extension of the little red dot population. The JWST has identified little red dots at redshifts up to approximately 10. The ELT will, by every careful description, push the detections to even higher redshifts. The combined ELT plus JWST observations will allow detailed characterization of the redshift distribution of the population. The distribution provides strong constraints on the timing of the cosmic phenomenon that produces the little red dots. The detailed shape of the distribution will, by every careful estimate, definitively test the cosmic timing predictions of the various theoretical interpretations. The fourth area of ELT observations will be the chemical composition measurements. The detailed spectroscopy at high resolution will allow precise measurements of the abundances of specific heavy elements in the gas around individual little red dots. The measurements will, by every careful description, distinguish between the various interpretations of the chemical enrichment puzzle. If the enrichment is local to the central engine, the abundance patterns will show specific signatures characteristic of accretion disk nucleosynthesis. If the enrichment requires earlier stellar generations, the patterns will show signatures of supernova enrichment. if the enrichment is from intervening absorption, the patterns will be consistent with normal galactic enrichment at lower redshifts. The fifth area of ELT observations will be the polarimetric measurements. The ELT will have, by every careful estimate, sensitive polarimetric capabilities that allow precise measurements of the polarization of the little red dot emission. The polarization provides direct constraints on the geometry of the emitting structure. The black hole star framework predicts low polarization for spherical envelope geometries. The alternative interpretations predict, by every careful description, different polarization signatures for different geometric configurations. The detailed polarimetric measurements will, by every careful estimate, distinguish between the alternatives. The cumulative ELT observational program for little red dots will, by every careful description, transform our understanding of these objects. The current observational picture is, by every careful estimate, substantially incomplete. The current best interpretations are based on limited data. The expanded observational data set from the ELT will, by every careful estimate, allow much more detailed and definitive tests of the theoretical frameworks. But the ELT is not yet operational. The first observations are expected in 2028. The full scientific program will develop over the subsequent years. The detailed results will, by every careful description, gradually emerge as the observations accumulate. The complementary observations from the GMT and the TMT, when they become operational in the late 2020s and early 2030s, will add additional capabilities. The combined next-generation ground-based telescope observations will, by every careful estimate, definitively characterize the little red dots and substantially refine the black hole star framework. The implications for our broader understanding of early universe astrophysics will, by every careful description, be substantial. The little red dots are, by every careful estimate, the leading observational example of the direct collapse black hole seed formation process. The detailed understanding of these objects will substantially refine our understanding of how the first supermassive black holes formed. The framework that emerges from all of this work will, by every careful estimate, transform our understanding of the early universe. The work is, by every honest description, in active progress. The next decade will be, by every careful description, a particularly active period for this area of research. The cumulative results will substantially clarify the picture. Let's bring all of this together as the night settles deeper around us. The little red dots that James Webb has been finding by the thousands at the edges of the observable universe are, by every careful description, one of the strangest discoveries in modern astronomy. The objects looked in the initial JWST observations like compact, dust-obscured, accreting objects. But careful follow-up observations revealed that the simple interpretation does not match the detailed data. The dust interpretation runs into specific problems with the mid-infrared emission, the spectral shapes, the polarization, the variability, and the inferred dust column densities. The starburst interpretation runs into specific problems with the broad emission lines. The dense cluster interpretation runs into specific problems with the dynamical stability. The modified accretion disk interpretation runs into specific problems with the compactness and the X-ray suppression. The cumulative observational evidence has, by every careful estimate, pushed the field toward the black hole star framework as the leading interpretation. The framework was originally developed by Mitchell Begelman at the University of Colorado starting around 2010. well before the JWST observations of the little red dots had even been imagined. The framework has been substantially extended by Kohei Inayoshi at Peking University, Roberto Maiolino at the University of Cambridge, Andy Goulding at Princeton, Anna Christina Eilers at MIT, and various other research groups in papers published over the past 5 years. The framework proposes that the little red dots are not galaxies in the conventional sense. They are direct collapse black holes in their growth phase, surrounded by enormous radiation-supported envelopes of gas that make them look superficially like compact, accreting objects. But they are something fundamentally different from anything else in the local universe. The black hole star framework explains the compactness of the little red dots through the size of the envelope, which is at most a few thousand astronomical units. It explains the redness through the photospheric properties of the envelope, with a characteristic temperature that produces the observed spectral colors. It explains the absence of mid-infrared emission through the absence of separate cool dust. It explains the broad emission lines through gas at the inner edge of the envelope. It explains the suppression of narrow emission lines through the absence of a normal extended galactic structure. It explains the suppression of X-ray emission through envelope absorption of the central corona. The framework predicts specific population-level properties that match the observed redshift distribution of the little red dots reasonably well. But the framework is not yet definitively confirmed. Alternative interpretations continue to be developed. The detailed observational tests are still in progress. The next several years of JWST observations and theoretical work will substantially clarify the picture. The implications for our understanding of early black hole growth are, by every careful description, profound. The little red dots are, in the black hole star interpretation, direct observational evidence for the formation of direct collapse black hole seeds in the very early universe. The seeds, with initial masses of approximately 10,000 to 100,000 solar masses, grew rapidly through accretion during the first few 100 million years of cosmic history. The growth produced sufficient radiation at some point in the process to support the quasi-stable envelope structures that we observe as little red dots. The envelope phase persists for the cosmic epoch, during which the gas supply conditions are maintained. Eventually, the gas supply changes, the envelope dissipates, and the central black hole becomes a more conventional active galactic nucleus, or a dormant, supermassive black hole. The implications for the cosmic timeline of black hole growth are accelerated compared to the standard stellar seed framework. The first supermassive black holes were already forming during the first few 100 million years after the Big Bang. The growth was faster than the standard framework predicted. The eventual masses of supermassive black holes in the local universe are easier to explain in the accelerated timeline. The early supermassive black holes that JWST is finding are the predictable consequence of the accelerated cosmic history. The implications for the black hole host galaxy connection are also substantial. The little red dots have very small host galaxy mass relative to the central black hole mass. The connection between black holes and galaxies in the early universe was different from the connection observed in the local universe. The black holes grew first, the galaxies caught up later. The eventual modern M-bulge relation was established gradually as the host galaxies grew around the already massive central black holes. The little red dots are, by every careful estimate, a transient cosmic phenomenon. They formed during a specific limited cosmic epoch when the conditions for direct collapse seed formation and envelope support prevailed. They do not exist in the local universe at all. They are observations of a specific class of cosmic objects that the universe used to make through specific physical processes that no longer operate. The strangeness of the interpretation is, by every careful description, exactly what makes it scientifically important. The little red dots are not familiar objects in unfamiliar conditions. They are something fundamentally new that we are observing for the first time. As you drift into sleep tonight, consider what is actually happening inside one of these strange objects. 8 billion years ago, at the edge of the observable universe, a black hole formed through the direct collapse of pristine gas. The black hole grew rapidly, accreting matter from the surrounding pristine reservoir. The growth produced enormous amounts of radiation which created an envelope of gas around the central object. The envelope extended outward to thousands of astronomical units, comparable to the size of our solar system, but with a central engine that was a 1,000,000 solar mass black hole. The object glowed across cosmic time, sending its light through the expanding universe. Tonight, that light has finally reached us, after travelling for 13 billion years. The James Webb Space Telescope has captured it. The light has revealed a class of objects that no astronomer working in the early 2022s had predicted. The objects are, by every careful description, one of the most striking discoveries of the JWST mission. The detailed understanding of what they actually are is, by every honest description, still being worked out, but the broad outlines are now reasonably clear. The little red dots are black hole stars, and they are stranger than anyone predicted. Sleep well tonight, and tomorrow we will continue to explore the deepest mysteries of the cosmos together.